We are about to start. Gents, please take your seats. It's really low. Wim Hendricks. Guys, take your seats. We're about to start. And engine should be coming any minute. So, welcome to Vancouver IETF 120, and we are opening Routing Working Group meeting. It's a very busy agenda today, so please be on time. Please come up, and we'll try to get 2 slots in Dublin, but for now it is what it is, so please be efficient, please cooperate. You're saying? So, anyway, so not well, by being in this meeting, you are subject to IETF standard process. Please make sure you are reading the documents mentioned here, you are aware of not aware, and you agree with them. So RFC since 119, none. We are still in process of working through. We have adopted 2 drafts, the multi-segment SD1 and rejuvenated designated source routing, which we are trying to fast track and actually get very quick to be ready for working group last call. We have submitted 3 drafts for publication. So thanks authors for working with us with working group to make it possible. BGP peak, dear editor, we really need you to address the editorials. Please help us to help you. QoS model, there have been many comments. We know that QoS data model is a very complex topic. There's many models as implementations. So we continue working on it. And we are at point to multiply BFD. We plan to start working with last call after IETF 120. Jeff?
Yes, wearing my BFD chair hat, please call that also in the routing RTGWG mailing list as well.
Absolutely.
Thank you.
Sasha, any questions? So again, as I said, we've got very, very busy agenda, so please cooperate with us and be on time. Linda.
Is this the Okay, so I just take this moment to give
I don't think it's going to work for you because it's from my laptop, so I'll be.
Okay, all right. So as the multi-segment SD1 through the cloud backbone, just major update since being adopted to working group draft. Next page. So here is basically the background. You have CPEs located in geographically far away distance, and when they have SD-WAN traffic among themselves and may go through public transit, which public internet, which can be slow, unpredictable performance. So you would like to dictate the traffic, steer the traffic through the cloud backbone. We call multi-segment SD-WAN because there's an SD-WAN segment from CPE to the first cloud gateway, and then from egress gateway to the destination. Next page. So So what it really does is really to steer the traffic, and the draft is proposing to use Geneve header because Geneve header is being supported by many cloud vendors. Um, and in the Geneve header, you basically list down the the where you want to egress the network, and maybe you will include some other sub-TLVs like include nodes or exclude nodes, so that it can help to steer the traffic to your desired destination. In this environment, from A to the source A to gateway, there could be multiple paths, could be IPsec paths, could be MPLS paths, but nevertheless, it's aggregating all those different underlay paths into one path, SD1 path, and then with the Geneve header to dictate how you want to steer the traffic through the backbone.
Not sure what happened.
Next page. Oh, so doesn't show it anymore.
Just give a second. Sure, coming up.
Okay. Mm, Next page. Next page. We finish this page and we go to the next page. Next page.
Gets stuck for whatever reason.
It doesn't go anymore.
See.
Oh, okay. So here are the major components. One progress we have made since last IETF, we got the multi-segment SD1 option class for the Geneve encapsulation that's already assigned by IANA. And underneath this option class, we have defined 6 sub-TLVs. Basically, there's endpoint where you want to egress, and there's originator, and there's also transit and include transit and exclude transit. And last one is about authentication. Actually, that authentication, we have a new draft in security area, and we present that at today's O dispatch and talk to the security ADs and to find the proper place to identify, to basically standardize how we do the HMAC-based authentication just for the header purpose. Next page. Okay, so here's the payload. We're just talking about data plan. The traffic itself, we're talking about transit traffic, because from CPE, they may have traffic to be terminated at within the cloud. That is actually through the SD-WAN path at the cloud gateway being terminated, and then services being served. And this is talking about transit traffic from A to B, both are CPEs, and you add the Geneve header to indicate this is transit traffic. And this header, the payload is already encrypted by IPsec. Here we are adding another authentication just for the gateway to authenticate the header, make sure it is not tampered. Next page. So here are some major changes, and since it's being adopted to the working group draft, we have basically enhanced all the writings, and thanks to Adrian Farrell's review and quite a few other people's review, make the document IFC ready and describe all the fields in the sub-TLVs. And we revise the illustration, how the traffic goes through the source to the first gateway, through the backbone, and egress, and to the destination. That's the major changes since being adopted as working group draft. We are hoping to get more reviews from the working group community, and that's it. Next page. So we also need some people who are expert in Geneve to do the review. There was a old draft which is expired. about Geneve, IPsec on top of Geneve, reaching out to the authors to see if for their review, for their expert feedback. That's the draft name. We need more reviews. That's it. Any questions? No? Okay.
Thank you, Linda.
Thank you.
Good work. Easy.
I don't think I'll take the whole 10 minutes. I'm just going to talk about some of the options we have now for revising the VRRP MIV, Yang model, and go through them and just bounce off the working group, the one I'm leaning towards. Next slide. So we recently completed, actually it was last year, RFC 9568, which revised the base VRP spec to have all the inclusive language. We changed it all. But once we did this, it was amazing the number of technical comments we got and the improvements we made, especially in the area of IPv6, because it turned out back when 5798 was done, there wasn't near the experience with IPv6 VRP and deployments, so we fixed a lot. And basically what we did is the big change that motivated it all was we now use the term active router rather than the previous term. Like I said, now that we've done that, we want to do the same for the VRP MIV, which really, as you can see, it's RFC 8347. I don't know of any accent implementations, but there's also some things to change in that as well. There's also a MIV, which is very old too. I don't know if we'll change that. Won't be me who does it, I can say that. Next slide. So here's the problem we have. Yang 1.1, as defined in 7950, doesn't allow identifier names to just be changed in revisions, because that would be a non-backward compatible change. So the way that you do it is you're supposed to deprecate the old and add the new, and then sometime in the future you can get rid of the deprecated ones. Well, the problem I have with that is the RFC cycles aren't that quick. We have had some, we've had some ones, at least in LSR, go through really quickly when it's just, procedural changes. But I'd rather do it in one cycle. Anyway, that's why I'm doing it. So there's three alternatives to this. One is the brute force approach. That's where you do the 2 iterations. You do it the way it was meant to be, of deprecating the old identifiers and defining the new, and keeping them both in the Yang model for at least one revision cycle, or one probably a couple of years or whatever. And then with a new RFC, you take out the old ones. The other one would be, this was one I had some talk, and I at least had one Ops AD on board with this. You just change them. You say, okay, we always said in Yang, we can make bug fixes that are non-compatible. So what we would do in this case, we would treat the non-inclusive language as a bug fix. And the third, this is an interesting one, I thought about updating this, is to just define a new Yang model. That's the old name. Actually, what this was supposed to say was IETF VRP -2. You'll see that. But anyway, so you kind of just, bring the mountain to Muhammad. Anyway, next slide. So here I just have, you can see the changes I made that you know, there's a type def, there's a couple identities, and the one thing, there are no config true leaves that are changed. It's only op state, but unfortunately, next slide. I guess I should have taken the clicker. It would have been easier on you, Jeff, but anyway.
I'll survive.
Okay. The one thing, there is a notification, which, you know, if somebody did implement this and we're following that, you know, you taking it out would be definitely not backward compatible, because it uses the new identity. It uses the current identities and types. Okay, next slide. So we already talked about this. This is the easy way. I mean, not the easy way, but the way that NetMod has defined to do it, of just changing them and keeping the old ones. I'm not going to say much more about this. And I don't like this one because it doesn't, you know, I'm doing a whole RFC, but I'm not really removing the non-inclusive language like we did in one shot for the actual base protocol specification. Next slide. Now this is the one about treating as a bug fix. And I've gotten mixed on this. I had one management AD telling me absolutely you couldn't do this. And I had a previous one tell me, well, maybe we could do this because they're not config true. But there was mixed. But I'm thinking this probably wouldn't, you know, this probably wouldn't be worth the controversy it would be called. And I'm thinking back to one time. I know right now we were talking about fixing the type def for IP address in the types, you know, the RFC 6991 in the viz document. And I advocated, okay, right now you can specify, the default is to specify a zone on an IP address, which means the default is to have like a % and then the name of the interface. The problem, I know there's a lot of people that use the IETF types in native models. There's at least one major implementation that uses it. But if you specified an interface on the end of these IP addresses, the transactions are going to fail. Well, anyway, we didn't decide to change these. We kept the old ones, and the solution was you change the models, the non-IETF models, to use the type that it was meant, IETF, IP address, no zone. So what I'm getting is I'm not very confident that it would be worth trying to get non-backward compatible changes through NetMod. Next slide. So here's the one I want. Here's the third, and there's a reason it's last. That's because that's the one that I think I'm going to try and do. We just change the name. We come out kind of like MIB2. Remember, you know, MIB1, MIB2. This is going to be IETF BRP -2 Yang. That way we can do it in one shot. We don't have non-backward compatible changes. I don't know of any implementations of IETF BRP. And final slide. So I actually had, I'd like to proceed with this. I actually had, just because it accomplishes my goal of doing this in one RFC cycle, and there's a an open source implementation routing stack that they were talking about. They asked me, well, what are we going to do on this? And I said, I'll know after the IETF. I think I'm going to go for it. That's the Holo Rust routing stack. Renato Westfall. He's got somebody who, not himself, but he's got somebody who wants to implement the Yang model for BRP. So this is the one I'm going to try and do. I guess we can talk about this on the list. I'll shortly after the IETF, I'll do the new version that uses the new name and requests the new identifiers for the new model from IANA. That's it.
Thanks, AC. And as a working group participant, I do support this approach. We want to reduce the amount of bureaucracy and number of cycles. As working group chair, we will kind of send to the working group list proposal and gauge the support and objections.
Okay, sounds good.
Thank you.
Hello? Am I being hearing?
Yeah, we can hear you.
Okay, thanks. Hi everyone. This is Fan Zheng from China Telecom.
So you can run your slides.
Oh, okay. Okay, thanks. I'm presenting the update of Young data model for ARP and a new draft of Young data model for IPv6 address resolution on behalf of the other authors. And the ARP Young model has been presented in routing workgroup like several times as I remembered. Since the last presentation was about years ago, we're going to recap what the ARP model covers. There is some basic ARP functionality in the IETF IP Young model that allowed you to configure dynamic ARP and static ARP entries. So this draft covering in the extra bits of ARP that are not in IETF IP, but lots of vendors have supported things like proxy ARP configuration, grid ARP configuration, and ARP packet statistics on interfaces. So what do we change this time? Mainly, it's been editorial improvements to improve the description in Young module and the security section. And also, Yongqing Zhu and I have joined in as new co-authors. And this is the current tree on the latest draft. And it's not changed since the last update. And next. The ARP Young model has filled in the gaps of IPv4 address resolution, but it cannot provide support for IPv6 since ARP is only about IPv4. So the address resolution of IPv6 is covered by Neighbor Discovery Protocol defining RFC 4861, which also covers the functionality like router and prefix discovery, and some related functions such as duplicate address resolution. DAD is defined in RFC 4862. So similar to ARP, IETF IP has covered dynamic and static IPv6 neighbor cache entry on and DAD on interfaces, defining like a list for neighbor cache for IPv6, a list for its router flag, and a list for the number of consecutive neighbor solicitation messages with DAD. And there is IETF IPv6 router advertisement, which is the submodule of IETF unicast routing, which is related to ND, but it only covers the configuration of router advertisement. Therefore, we need another Young model to cover the rest of functions of ND that are not covered by the above Young model, but a lot of vendors have been supported. In this new draft, we define IPv6 Young model IETF ND to support the configuration of ND, especially about address resolution of IPv6 and related function like proxy and proxy neighbor advertisement, NUD, DAD, and NG packet statistics on interfaces. This is the current tree of IETF ND. As you can see that we defined the container for ND for global configuration and per interface configuration, which augments the IETF IP. As for neighbor cache entries, we define stale timeout globally and per interface. It is the timeout for neighbor cache entry in stale state. A stale entry will be discarded if it's still in stale state after the stale timeout is passed. And the node age augments the neighbor cache list defined in IETF and IP, which is the time has passed since the last reachability confirmation for the neighbor. And the dynamic discovery enables the dynamic IPv6 address resolution on interfaces. We set this enabler considering the risk of hijacking of dynamic address resolution. And as for NUD, we define the node NUD to enable the function on the interface, and reachable time for the time that's considered a neighbor reachable after receiving its reachability confirmation. The NS interval is the interval of retransmitting NS messages of address resolution, NUD, and DAD, also known as retrans timer in our FC 4861. The container proxy NA includes enablers of two different types of proxy. The interVLAN proxy enables router proxies for hosts in the same subnet with different VLANs, and all proxy enables the router proxies for all hosts, which means the router will respond to NS messages with its own NA message, no matter what the original target is. And last, the container statistic contains the ND packet statistic on the interface. And that's all. And any feedbacks and comments are welcome, and it will really help us improve the draft. And we would like to ask for adoption of the IPv6 address resolution young model draft.
Any questions?
So the app young model draft was a working group document for a long time, but it was expired. So now we have a new editor that's committed to drive, push the work through. So we will continue that work. And then I also added a new draft for IPv6 address resolution that I think is useful. So we'll try to start working group adoption call for the new draft. So please review and send your comments if you have any.
Thanks.
Thanks.
Thank you.
Jeffrey, do you want to present now or later?
Yeah, because we'll go to the number 6 instead of 5 because Jeffrey need to be away for. Yeah. So no. Yeah.
Wait, hello. This is Fang. Can you hear me? Hello, can you hear me?
Yes, we can hear you. Yeah, and you have control of the slides.
Okay. Okay. Thank you. So I'm Feng Yang from China Mobile. And I'd like to share some thoughts on how we can transform the SRv6 technology into some network services, some ideas. This presentation is by me and Chan Wangling from H3C. So why we do this? we have some kind of observations. First is that we see two important pieces of information. The growth of internet traffic has slowed down, and the second, the IP SRv6 is being rapidly deployed worldwide, and we China Mobile's IP networks has been upgraded to the SRv6 last year, and we are exploring uh, how to convert SRv6 capabilities into service offerings that can generate the revenue. We can see some of the uh, our revenues. Most of the revenue come from the to C and to H services, and some of the revenue come from the to B. The to C is from the mobile user, and to H from the residential users, and the to B is from the business government incomes. Uh, for uh, but but the problem is after we have upgraded the network from the IPv6 to SRv6, and how we can turn the technology uh, into some more kind of the services, because when we cannot, because SRv6 can only run in the limited domain and cannot be uh, running on the last mile, which is outside of the limited domain. So we need kind of the mechanism to uh, to to meet this requirement. Uh, the basic mechanism we needed are the traffic classification and traffic steering. Uh, we but but for those two mechanisms, there are some existing tools. We have listed some of the tools existing, but all of those tools cannot meet our requirement. For example, Qs is not trusted when it carried from the external limit domain, and ACL are not scalable, and DPI raised some privacy concerns, and NSH are not recommended because it's only running in the limited domain as well, like SRv6. So we need a new mechanism. It should be trustable, scalable, and simple, and some others, like it can be cross-domain, support cross-domain. So we have
Frank,
some.
Would you take question now or at the end of the presentation?
It's a very quick question. AC Lindum,
Okay.
I'm not familiar with this 2B, 2C, 2H nomenclature back on that slide. What does that mean?
Okay, the 2B means some of the network services are provided to the enterprise and government.
Oh, is that like a classification that
Yeah,
in industry that I should know? I don't know. Okay, it was just
yeah.
So usually those
And
are B2B, B2C, and so forth. So business to business, business to customer, customer to business relationships.
oh, that's B to B, not to be. Okay.
To be or not to be.
so the 2C is to the product for the mobile user, and 2H is for residential users. So we have some ideas about to share. Here we propose our solution, which is called ARN, an application responsible network. Maybe the name is not very good, but we just call it at this moment. it is an intermediate layer between application and networks that encapsulates SRv6 network services applicable to MPLS as well. By carrying the AR, ARN has also has an ID which called ARN ID. Is it can be carried in the application's DOH payload, that is destination option header. It is provided a data plane API interface. By this, actually the ARN ID, we have the user side ID and the network side ID. Let's maybe the picture is not showed very nice. Let's take a look at the overall process and see how ARN works. On the left side, we are I want to talk about how it is allocated. In most cases, the first step is network service require network service almost planned in advance with a predefined slices or passes, which can be associated with network ARN IDs and be configured in advance on edge network devices. Step 2, when a user subscribes to a network service, such as low latency service, the operator assigns the locally unique user ARN ID associated with purchased network service. The network ARN ID and configuring it on the backbone network services. Then I will show how to. On the right side, we show how to use ARN ID. So the step 3, the user can encapsulate the user ARN ID for specific applications as needed. Currently, we carry the ARN ID in the DOH. And step 4, backbone edge device map to the user ARN ID to the network. Map the user ARN ID to the network ARN ID upon the receiving the packet. Furthermore, it will map it to the corresponding network services, for example, the slice or the pass. This enables applications that do not support SRv6 to call the network services. Then some more share about the security and the privacy. User ARN ID are randomly generated for each subscription. They protect user data privacy, and the network services are encapsulated via the network ARN ID, invisible to users. Thus protects the internal network information from exposure to outside. During the mapping,
You've got
mapping
5
of
slides and 3 minutes
user
to
ARN ID.
finish.
Okay. During the mapping of user ARN ID to the network ARN IDs, access control can be implemented, such as we can prevent the unauthorized user to do the programming of the ARN ID. So the basic framework is simple, we have the controller and the user edge and the network edge services, network devices. So the user ARN ID can be generated by the application or the user edge devices, and the network ARN ID and the user ARN ID mapping are done on the network edge devices. This mechanism can also support the cross-domain interoperability. So we at this moment we have put the ARN ID into the DOH function. DOH extension handler, and we have three kind of the AI IDs. One is only encapsulates the network capability, and also the other one is encapsulates both of the like the middle of the right hand middle of the picture shows, which both has the network and the resource AR ID. Resource here means some kind of the cloud services, and we in the bottom right one that is only for the cloud services without the network services. So we have some use cases here because the time we have run out of time, we are not able to go into more details. So the basically in this page we have briefly show how we how customer can subscribe the their ID and how we can get both of the directions of the traffic can be speed up. And last we are doing some kind of lab test to verify our idea. We have several vendors to implement in the devices, and we are done this work in this year. And last one, and comments. That's all.
Any questions?
So right now in RTGWG, we have proposals for APN ID, ARN ID, service ID. So I guess we need to consolidate the idea. First of all, figure out whether they are useful, the use case for them, and then work on a consolidated solution, not all kinds of IDs.
Selim?
Yeah, thank you.
I've just looked at, I mean, I just looked at the draft. I have to admit, I haven't participated in all the discussions. I know there's been BOFs in something else related that had application in the name and everything, this kind of going. And I'm wondering for what these, I just saw the use cases. What is the advantage of this over just assigning a behavior to a SID, to an SRv6 SID? The existing of actually inventing a new identifier and putting it in the header of every packet.
So the quick answer is that let's go to the second page. We have problems that SRv6 that is running in the limited domain, and we want to change the to have the SRv6 to define some kind of product can sell into our customers. So because you cannot run in SRv6 on the last mile, which is outside of the limited domain, so we need some kind of technologies to invoke the SRv6 pass.
So then you'd get standard behavior for these ANRs or ARNs across. You'd you standardize these, right? That's what you're saying, and they'd mean the same thing to everybody. Is that what you're saying?
Yeah.
Yeah. Joe, you are please.
Thank you. I do understand the difficulty of classifying customer traffic at the edge. And part of this presentation seems to be a request for a new field that the customer can specify from the customer CPE to the operator provider edge router, so to simplify classification. So my first question is, why is that a field any more trustworthy than allowing, let's say, a DSCP on that same link? It seems like the existing identifier technologies either have the same problems of trustworthiness, or I'm missing something about why this works better than the existing identifiers.
But yeah, the because as we as, the reason is that the queues, like for example, DSCP does not carry any kind of the uh, user information. Because you know all of the DSCP is standardized, and every value has a specific meaning. But
Oh,
here we
there's
have
no. DSCP is a 6-bit field, and there are recommended meanings, but not required meanings.
well, yeah.
Now, if your argument is that 6 bits isn't enough, that's a reasonable question. But let me then state the other half of the question. If you assume you need something new to identify what the request is from the user, and you have some way of knowing the user is allowed to make this request, and you need more values than a DSCP, it still seems that within your network, you could use MPLS SIDS, SRv6 SIDS, or any number of trustworthy technologies. You don't need a network ARN-ID to go with it, even if you need a new user ID. That
Actually,
relates to AC's question.
yeah. Let me some explanation on this. The first, we cannot use SRv6 SID is because SRv6 is only running in the limited domain, and we want to run it outside of the limited domain.
Well, but your network, the network ARN-ID, is within your limited domain.
No, because ARID can be encapsulated by the customer.
But
For example,
I thought you said the user ARN-ID is encapsulated by the customer.
yeah, yes.
But the network ARN-ID is not for the customer's use unless you're allowing the customer to direct traffic, and that gets you into a whole new set of problems. You asked why is NSH not recommended? It's because you can't trust the customer to direct traffic across an operator's network.
Yeah. For your network side, we because we want to support cross domain. That
Do you mean between operators?
Joe, guys,
Yeah.
please move the discussion to the list. We are running out of time. It's all valid questions. Joel, please do send your questions to the list. And it's not
Yes.
only applicable to IRN, it's applicable to all other application ID frameworks. And
You gave these guys time, so I asked them.
sure, I understand. Please do send it to the list. Jim?
Yeah, just a comment. To be honest, it was a little difficult to understand remotely what's trying to be done here, but a couple of things jumped out, and that was talk about network slice and talk about interfaces from customer to the network. And it just struck me that there's a whole bunch of work that's been done in the TEAS working group that they might want to take a look at. Unless I'm completely missing the point of the presentation.
Okay.
I would really appreciate your reaction on the list and try to address all these questions. Yeah, they've been brought in before with different kind of application layer IDs, and they need to be answered before we can progress.
Okay, thank you.
Thank you. Who's sharing? Yeah. You have the control of the slides. Please go ahead.
Okay, thank you. Can you hear me?
Yeah.
We have the
Okay.
timer.
Hi.
Stay, yeah. You
Okay.
have 10 minutes, so please stay to the timer.
Sure. Hi, I'm Yoli from ZT, and my presentation is about adapter routing notification for load balancing. So, adapter routing is a routing mechanism which makes dynamic routing decisions based on changes in network load status. And adapter routing can be local or remote. For local or adaptive routing, after congestion occurs, the node decides the traffic to be rerouted and it changes paths locally. And the remote adaptive routing is used when there's no other uncongested paths available locally. And adaptive routing notification, which is also called ARN, is generated and sent to upstream nodes. Then upstream node changes the traffic path accordingly. As we can see, for remote adaptive routing, the ARN is an important element. And this document provides analysis on different ARN mechanisms, including the information carried in ARN and how they are delivered into the network. Some key points should be taken into consideration for changing traffic paths remotely triggered by ARN. For the local nodes, it should decide which remote nodes should the ARN be sent to. This determines the destination address of the ARN message. For the remote node, first it needs to know which traffic's forwarding table needs to be adjusted. In most cases, the traffic identifier carried in ARN can help to locate the corresponding forwarding table. Secondly, the AR node needs to know which port in the traffic's forwarding table needs to be blocked. The information can be carried directly in the ARN or indirectly indicated by the ARN. Following are some ARN options. For option 1, the ARN is sent to the upstream node along the reverse traffic forwarding path, and the upstream ARN node treats the ARN receiving port as the original output of the traffic on it. Below is an example. A traffic 1 is sent along the red-colored path from S7 to S10. On S6, when traffic 1 is received, S6 records the traffic identifier and the receiving part of it. When on S6, when congestion occurs and it decides that traffic 1 should be rerouted, S6 checks the local traffic records for the receiving part of traffic 1, and then ARN for traffic 1 is sent to the upstream node S2 via the receiving port. For S2, after receiving ARN, if there's other non-congested paths available, it will block the ARN receiving port in the forwarding table of traffic 1. If there's no other paths, S2 should further send ARN via its own receiving port of traffic 1, which means S2 needs to keep the receiving record of traffic 1 as well. About the pros, there's not too much changes for the routing and forwarding procedure. And the main cons is that it's a stable solution. The records need to be maintained on the local device for every traffic requiring adaptive routing notification. And for option 2, the ARN is sent directly to the nearest upstream node that is able to perform AR for the traffic. And the original output of the upstream node of traffic is carried inside the ARN in this case. So when S7 receives traffic 1, since there's more than one path available for traffic 1, it chooses one output for traffic forwarding and puts its device ID and output ID into the traffic. For S4, the procedure is similar. It replaces device ID and port ID in the packet with its own. And then on S2, suppose that there's only one output. S2 will forward the traffic directly without modifying it. So on S6, after congestion is detected, S6 would send ARN directly to S4 with the device ID and output ID obtained from the traffic. And S4 would block the output for the traffic accordingly. In this option, no traffic receiving records is stored locally, but the packets of the traffic need to be modified when being forwarded. As we can see, the AI mechanisms require devices to consume additional resources. And ARN is not necessary for all traffics in some networks. For example, rerouting small flows has not much effect on relieving the congestion compared with large roads. So in this document, a ARN tag is introduced. The only tagged packets are processed additionally for ARN after traffics are received, and ARN are generated only for tagged traffics after congestion. So here's a summary. So the definition of adaptive routing varies in different contexts. So in this draft, adaptive routing is regarded as a fast partial path adjustment mechanism in response to sudden traffic imbalances caused by network events. And ARN tag helps to reduce the processing burden on the device due to enabling ARN. Next steps. And there are still some ARN options uncovered in the document. For example, setting ARN by multicast. We'll add them in the future version and welcome feedbacks and comments. Thank you. That's all.
Sasha?
Sasha Weinstein. I haven't heard anything about loop avoidance with this scheme. How can it be provided? Maybe I have missed something, but you change routing on the fly for part of the traffic, for all of the traffic, doesn't matter. How can you guarantee that the scheme is loop-free?
Yes, this is one point that is under analysis in the draft. So when you change in the remote path at a single point, you may cause the switch path still passing through the congested link and the loop. So especially when especially when the network is more than 2 tiles. But after further ARN and the path adjustment procedure, the link can finally be adjusted. And one option to solve this problem is sending ARN via multicast. So the related nodes in the network can adjust their paths accordingly. But how to control the scale of multicast should be considered, and not all the network operators want to introduce multipath traffic into their network. So this point would be further described in the future version. And thank you.
I may have missed something. I'm not sure I understood your response. Let's take it offline on the list. Thank you.
Okay, thank you.
As a working group participant, if the reaction on IRN is to block port, you'll oscillate. You'll block the next port that will become best path towards destination, exactly in the same way you create congestion before. So it definitely needs to be done per traffic class on the port, not per port. Introduce yourself.
Yeah, Dan Bogdanovic. We have so many QoS mechanisms that are not being used. So for me, this is just another QoS mechanism, and what are the chances for this to get used, really?
So generally, compared with other QoS mechanisms, so at least in this document, the adaptive routing is seen as a partial path adjustment mechanism. and it can be used together with other load balancing mechanisms. For example, you first you can use the network controller plans and controls the traffic paths globally. Then when the congestion occurs, you can use adaptive routing to respond quickly by adjust the path partially. And then the controller may then make global adjustment so afterwards. So maybe I can further further analysis in the comparison with this mechanism with Qs. So in the future version.
It would be good topic to discuss on the list, especially the loop avoidance, the lock avoidance, and how can you use it in a way you don't oscillate between ports, creating congestion yet on another path. Jeffrey?
Yeah, thank you for your comments.
Okay, so this is a draft between with collaboration on several organizations, including Kevin Wang, Jeffrey from Juniper, and Chang Wang from New HCC. Router info advertisements. Some quick background is that back in the last IETF, there were two presentations and drafts that related to this. The first one is the draft 1 IDR next hop nodes, where we would consider the next hops the load information when you do the load balancing. And another one is draft Liu in the passive-aware remote protection. Basically, they rely on the quick notification of remote downlinks for fast reroute purposes. In both cases, we require fast flooding of link or neighbor or path information outside the routing protocols. So the goals of this is to specify a generic way of doing that, flooding router information outside the routing protocols and make it easily extendable and make it hardware friendly. For example, certain information could be sourced or handled in the ASIC, things like that. We do not try to reflood information as is. For example, if you receive advertisement from one neighbor, you try to reflood it as is to some other neighbors. You could consume the information and generate your own advertisements flood to other neighbors. That's fine. But that is not the concern of this document. This document just tries to define mechanisms to do the flooding. We also do not try to specify how often the information is flooded and how the information is returned and used. We just provide a basic message bus. So this is basically a UDP-based flooding. We would get a new UDP port. We have the versions number specified here with some reserved bits there and flag bits. The main information is encoded as TLVs. And authentication and acknowledgement, they are all optional. Because this is UDP based, so fragmentation is theoretically allowed, but it's unlikely to be used because we quite often we would want the information to be timely flooded and handled. So you would just send multiple messages instead of a larger UDP message. So I'll skip the authentication or part there. It's very similar to how it is done with the BFD. The destination address of those, the message could be one of these four situations. The first one is the IPv4 multicast address for all the routers on this subnet, or the IPv6 version of that. It could also be a local or remote unicast address and a non-link local multicast address. so that you can flood the information to a whole bunch of the receivers using the underlying multicast. I mentioned that the message body could include a lot of TLVs to include the information. One example is the neighbor pass information TLV. Basically, you just encode a bunch of neighbor records, and each neighbor record includes a neighbor ID and 8 bits encoded information. I will talk about that encoded information later. Similarly, we could have a link info TLV that encodes a whole bunch of per link records. Each link record includes a link ID and encoded information. Here, the encoded information is 8 bits. For now, we only defined value 0 just to indicate whether the link or path is up or down. This is used for the situation where we want to use the remote link up and down for fast reroutes. Other values will be defined in the future. For example, we could encode the load information so that you can use it to do load balancing considering your next hop's load. We need some further discussion and agreement on this. So in this current version, we don't encode that information yet, but it should be easily extendable. Acknowledgement. So when you flood a piece of information, you may simply require the receiver to acknowledge back, or you just keep refreshing. And when you do want acknowledgement, you just encode a sequence number, and then the receiver is supposed to receive acknowledgement back. Otherwise, you just refresh, and the receiver will just age out the information they receive. The sender can change the refreshing rate either on its own. For example, the information that is flooded, it keeps changing, right? Depending on the changing rate, you may change the refreshing rate. Also, you could change your refreshing rate reactively. For example, you're flooding very fast initially, and then you get a complaint back from someone saying, hey, I cannot handle this much, and this is the rate I want you to do. Then based on that, you can also adjust your refreshing rate. Okay, so if acknowledgements is required, then you set a sequence number in your message, and the receiver will send back a message. Inside that message, there will be an acknowledgement TLV, including the sequence number for the message that it's acknowledging for. And refreshing rate notification. If a receiver cannot keep up, it can send back a notification saying that, hey, please slow down or something like that. So that message will contain some TLVs for the refreshing rate notification. The value of the TLV will include other TLVs for which we are requesting the slow down the refreshment. Finally, another use case is that excuse me. There are some use cases that people are talking about where a router may request its upstream saying that, please do not send me traffic for this flow. And this could be used for that purposes. So we basically send a 5-tuple in that redirection TLV, just saying that, please don't send me for that purposes. So this is, we're trying to design this as a very extensible and very generic way. And basically you can define all kinds of TLVs to encode the information you want to flood. The next step for this work is to add security considerations, especially when we want to flood this information to a bunch of remote receivers using multicast, or even unicast. As long as it's multiple hops away, we have some security considerations, but typically the use case for this is in the walled gardens. So shouldn't be too bad, but we do need to have some security considerations put in place. And also how do we advertise load information that we need to address in future revisions. In the meantime, we want to get comments and suggestions from the working group and have some discussions and maybe collaborations on this work.
We do have people in the queue, so yeah, go ahead.
Hello, Anton Sancourt. I have maybe a very naive question, but when you define the messages that you are using, I was wondering why you don't piggyback a link state routing protocol, because it seems a natural extension to link state routing.
There are two reasons. One is that quite often those other flooding for the use cases here needs to happen very, very quickly. We don't want to bother link state protocol with that kind of load. And another reason is that there are some concerns with using routing protocol as dump truck, and this is also something that we want to avoid. So this is basically another mechanism that goes on the side of the routing protocols.
Thank you.
Hello, Nangang from Huawei Technology. Can you jump to page 12? Yeah, next page. No, about the flow redirection. Okay, yeah. I'm a little confused on the use case of this TLV. It seems not the router information. Can you explain more how to use this TLV?
The specific use case for this one, I don't know if Chang Wang is here. He can probably explain it better. But at least the design use case for this is that a router is receiving traffic for a certain flow, but it realized that it cannot handle it for whatever reason. He just wants other routers to stop sending traffic this way. So he just used this one. Whether this use case is valid or not, and whether we want to put this into this protocol here, that can be discussed. But this is at least the one use case that the people have thought of using this flooding mechanism.
Okay, the information is flooded to over the network. Maybe there are some other tools to install the a rule of blocking a specific flow. Okay, thanks for your explanation.
Just one clarification. This flooding is not to the entire domain. It's basically you just flood to your neighbor. And
okay, I understand.
Yeah, yeah.
Okay, thanks.
AC?
AC Lindum Lavin. Yeah, I see this as a lot the same of some other mechanism, but it is a little bit different. Is this information, it lasts, is there actually an adjacency of your neighbors, or is there any relationship other than you save the information, or is it kind of stateless? There's no session state, there's no adjacency or session state, right? Or is there?
Right now it's just.
It looked like it was just, it looked like, you know, and there's also this thing in LSVR that, I see Randy's not in the room. The L3 link state, you know, the discovery protocol with, that has all the security and all of its in implementation already done. So there's a lot of overlap here of a lot of things, you know, and, you know, both ISIS and OSPF, we do have the link scoped LSAs, but there is more overhead in them because they persist until they time out or whatever. You know, it's like a piece of state, whereas this seems to be more like, okay, you just tell people about this and they retain it until it changes or until it could be like a one-off too, right? You could tell somebody, okay, do something, right? Too.
Correct.
Yeah.
It's a lot similar to the IGP's link local flooding, but we don't because this is could happen very, very quickly. In some use cases, people are talking about millisecond level flooding, and we obviously don't want to bother IGP with that.
Well, you know, there's been some proprietary uses of BFD where they put other stuff in it.
Yes, we
consider.
So
I'm not saying that's a good idea, but it has.
We are really over time. Oh, sorry. Tianji?
Tianji, CMCC. Some clarification question here. It seems to me, if better if you can show some picture about how you're going to set up these things, because when only reading your slides, I don't know how you are going to create those over the top neighbor or adjacency. Is that all being created statically or dynamically on demand? All kind of a control plane information here.
Sure. The two other drafts I mentioned at the very beginning, they sort of implies the use cases for this. And they do not talk about the remote flooding. I have another draft that has not been published that does talk about the remote flooding. I think I will publish that soon. That should provide some example on the remote flooding. But other local flooding that the two other drafts I referenced to earlier does provide some information.
So the session or some receiver or some server or whatever things will be configured on a router to receive the flooding information from the sender, right?
Right. If you don't have if you don't have this configured, you will not care about the UDP port.
Yeah, thank you. That's what I want to know. Thank you.
Okay, thank you.
Thanks, Jeff. Kind of general comment. We've been having the fast notification frameworks in this working group since early 2000s. There are probably about 10 drafts published over the last 20 years. Let's try maybe to do a interim and review of the solution, because what everybody is trying to do is to tell your upstream, don't send traffic to me. Either send it to someone else or just don't send it to me. There's a variety of solutions that involve control plane, involve just forwarding. Probably it would be good to do some consolidation and see where we are going as a working group with this. And again, granularity is important. If you block in another port, maybe it's not a good idea. But then you need to understand what to block, less loaded port. There's difference between different traffic classes, between different queues. So it's much more complex than just blocking the port somewhere upstream.
Okay, let's go to the next presentation. So who will be presenting the next one?
I will present. Hi everyone, I'm Jiaming from China Mobile. What I'm going to talk about today is adaptive routing framework. First is the problem analysis. In many cases, ECMP flow-based hash may lead to high congestion and variable flow completion time. For example, in the first figure, the link forwarding packet with color orange is more likely to be congested. Besides, due to the lack of congestion awareness, the load on already congested link might be exacerbated, as is shown in the second figure. A3 is unaware of the link. A2 to A4 is already congested. Continue to send packet to A2. It will increase the congestion level of that link. Additionally, the current load balance mechanism has no ability to distinguish the large flow from small flows. So if there's two kind of flow arrive simultaneously, ECMP will distribute them evenly across equivalent paths, leading to load imbalance. There are some possible solutions to solve this problem. First, we can increase the flow entropy by refining the granularity of load balance algorithm, such as based on cell package or flow light, so that the flow could be distributed more evenly. Moreover, after perceiving congestion, the device could change the flow characteristics like five tuple or IPv6 flow label to prompt a rehash or reroute. In addition, adaptive routing based on network state measurement also could be adopted. Select the optimal path according to the real-time network condition, and this approach also is what I'm going to introduce today. So, what kind of abilities does an adaptive routing mechanism need to have? First, to achieve even load distribution per flow load balance and per packet load balance could be performed. And each packet perform congestion detection, including link-based detection and flow-based detection. Upon detecting the congestion, notification should be sent to the remote devices to perceive congestion at earlier nodes. Respond to their congestion notification. Congestion adjustment could be performed by adjust path weights or path loads or by redirecting flows. And based on the information analysis, we proposed an adaptive routing framework consisting from 4 parts: routing plan, forwarding plan, adaptive routing policy, and the remote congestion detection. Routing plan is responsible for the transmission and calculation of routes. Besides the local information from a remote link should be included to calculate routes for the global congestion awareness. The calculated routes and the remote path info would be adapted to the forwarding plan. And forwarding plan is responsible for path adjustment based on the mode of adaptive routing and the remote link congestion information. And the traffic is forwarded following the adjusted forwarding table. Then is the adaptive routing policy. It is responsible for dynamic adjusting routes according to remote link congestion information or flow information and adapting the forwarding plan. The last is remote congestion detection. It is responsible for detecting link congestion and sending congestion notification to neighboring devices. So specifically in the routing plan, when calculating routes, the paths need to be perceived and the path information will be attached to the next hop. For the BGP-based network, remote path information can be the BGP identifier corresponding to the next hop. It can also be the BGP AIS path information or BGP route ID. For IGP-based network, remote path info can be the interface information from the next hop neighbor device to the next hop device, which could be the interface index or the local address of the interface. In the forwarding plan, the forwarding table is maintained based on the routing table provided by the routing plan, and it could dynamically adjust the weight and the load value of forwarding table according to the local and the remote link quality, as well as the payload of forwarded packets, and generating an appropriate flow table for flow-based forwarding and performing load balance during packet-based forwarding. here is some adaptive routing policy specification, and adaptive routing policy could be categorized into flow-based and packet-based adjustment. The flow-based adjustment mode could be further divided into weight-based dynamic ECMP flow adjustment and flow redirection-based adjustment. Weight-based adjustment mode is for link level congestion events, adjusting the pathways to avoid the congestion for subsequent flows. Flow redirection mode is for specific flow congestion events. The congested flow is redirected to ECMP link with lower loads and sufficient bandwidth. In the packet-based adjustment mode, the load on corresponding link is dynamically changed. Each packet will be sent through the link currently with latest load. And the potential out of issue within the same flow is resolved on the application receiving side. And for congestion control, congestion detection perceives congestion event by monitoring link buffer, bandwidth, and queue size. Upon congestion, send congestion notification to neighboring devices. The notification information can be of two types. Path information, 5-tuple information of the congested flow. Here are some examples of their 3 adjustment modes. In weight-based adjustment case, as is shown in the figure, when leaf 4 advertise the network segment 20.1.1.0 with mask 24 to 20.1.32.0 with mask 24, where BGP to all spans. The span will advertise their network segment with the next hop 8.8.8.8. Then forwarding table will be created on leaf 1, like the top right diagram, and it contains the remote path information. With span 4 detect a change in congestion on the link span 4 to leaf 4. The information including detecting node span 4 congested link span 4
1 minute to go.
Okay. Congested link span 4 to leaf 4, and the congestion level will be notified to its neighbors. After leaf receive this notification, it will look up the local forwarding table based on the path information and reduce the weight of corresponding forwarding entry from 25 to 10 according to congestion level. By the process above, the new traffic will be forwarded in updated proportion, and thus is the congestion. Here is the example of flow redirection mode. The first line is the characteristic of flow, and if this flow caused the congestion, and span 4 will notify congestion event to neighbors with path information and the flow feature. After leaf 1 receives this notification, it will increase the load of corresponding forwarding entry from 10 to 100, for example, according to the congestion level. Additional, locating the corresponding flow table based on the congestion flow information, leaf 1 will redirect the congested flow to the least load path, maybe from span 1 to leaf 2. Here are the examples.
Your overtime. Your overtime, please finish up.
Okay. Here are the example of packet-based adjustment cases. So the same forwarding table, same congestion event, and the same notification is sent. After receiving notification, leaf 1 looks up the local forwarding table based on the past info and increase the load of corresponding forwarding entry from 10 to 100 according to the congestion level. Therefore, the subsequent packet will be we prefer to choose non-congested passes. That's all my presentation. Any question?
Done.
Yes, Dan Voyer, back Canada. Did you think of a way to support that once the flow move by congestion, like having some kind of a way to trace it for the people supporting the network? Is it part of your initiative? Because I haven't seen it in your document. I guess not.
Thank you.
Anju?
Hongyi, you are next.
And Hongyi from Huawei. You mentioned several times adjusting pathways or path loads, and so what's the difference?
The weight is the ECMP weight for the weight-based adjustment. If the link is congested, it will the neighbor will adjust the weight of the link, and the load means the remaining bandwidth of the that link. So if you lower the load, if you increase the load of the link, and and the flow will not be forwarded in that heavy load path.
So the load value is set manually. It is not detected by some mechanisms.
It is adjusted according to the congestion level, and the congestion level is determined by the congestion point.
I think we need to move AC, please.
It's quick. I'm at AC Lindum 11. I was just going to say there's been other drafts at this IETF about how to handle per packet ECMP, but this draft this framework just makes the assumption that the big flows can be done per packet, and the problem is pushed on the application of packet reordering. But if the flow is that big, that means it's an awful lot of reordered packets that they're going to have to do. I think that hand waving isn't going to work.
Yeah.
Maybe we should move that.
I think we should take it in any way. And please do remember, if it's a data center, your RTT is 5 to 10 nanoseconds. By the time BGP sends an update with updated weight, you are much past congestion. You're either completely dead or free, right? So your control loop timing is crucial here. And I don't think any control plane in general would be capable notifying upstream nodes there's a congestion, right? We're talking about 2 orders of magnitude in timing. Next presenter.
Okay. It is in the chapter about the framework for Okay, thank you. This is the chapter for the framework for implementing lossless techniques in wide area networks. So first is abstract, and this document proposes a comprehensive framework to address the challenges of efficient, reliable, and cost-effective large volume data transmission over WANs. So the framework focuses on the planning and managing traffic paths, network slicing, and utilizing multi-level network buffer. And then aggregating instruction. And in the last IETF 119, we just highlighted several critical large data transformation use case that we emphasize the necessity of low packet loss and high throughput in WNs, such as scientific research, financial transactions, and multimedia content delivery. So we think the characteristics and the requirements of a large data transformation are listed as follows. First one is the large volume. And the data sets involving these transformations often reach terabyte levels. So enterprises need a large volume broadband dedicated line for the large data transformation. But it's very expensive, so the enterprise must be balanced the need for high capacity data transformation with cost consideration. And the second is the timeliness. And timeliness is a critical factor for data transformation over WNs, such as genetic research. Delays in data transformation can render the data obsolete, leading to incorrect results and conclusions. So timelessness needs high capacity broadband for the large data transformation. And then the third characteristics is the predictability. Due to the predictability, we can planning and managing traffic paths. It helps in optimizing resource allocation, minimizing congestion, and enhancing overall network performance. And so due to the characteristics and requirements of large volume data transformation, we have some challenges. The first one is the limited. The first factor is the limited network capacity, and it leads to the traffic conflicts, which may result in queuing and jitter. The second one is congestion hotspots, so we already need a packet retransmission. It will lead to latency and reduce the network throughput. The third one is the inefficient buffer utilization. And local devices buffer can't meet the bursted traffic. It may result in packet loss. Facing the challenges, we propose the solutions as follow. The first one is the adapt planning and the management of network resource. We can allocate a network resource based on sharing network information. So we can do the four things, to do the three things: network resource reporting and user request. Network devices report attributes such as bandwidth, latency, and buffer capacity. We can through the control plane protocols like the IGP and BGP-LS. The second one is the network resource allocation and policy distribution. Controllers calculate out IP-based dedicated lines. Just like the IP tunnels with the segment routing within the one domain based on available and flexible bandwidth and buffers. We can using the SR policy. Data traffic is steering into the IP tunnels at ingress nodes and directed to the dedicated network slicing. The third one is network state measurement and telemetry. We need a real-time resources measurement based on measurement packets, which helps in sensing utilized and available resource on network links. The second solution is the use and management of the multi-level network buffers. We can advance the congestion management strategy, which are necessary to coordinate the buffer information among the devices across the network. We also need the three things. First one is the single device buffer sharing and management. This is the premise of the buffer coordination. In nature, buffer resource information can be managed by the controller or exchanged through the control plane protocols like IGP and BGP. The second one is the cross-device buffer coordination. Given the nature of large data transmission, a single device buffer might be insufficient for absorbing bursty traffic. Therefore, multiple device buffers of the same fine-grained type, e.g. the same priority and slice, should be used collectively. So in the technology, we should define control signal and the trigger conditions for buffer coordination. And the third one is also the network state measurement and the telemetry. Here we will measure the buffer size. Okay, the third one is the requesting source rate control. If a network device can't solve the congestion problem itself, we should use this solution. Network devices can send rate control request to the source via data packet marking or separate control packets. Okay, finally, we give the conclusion. The proposed framework addresses the challenges of large volume data transmission over wines. We can use the enhancing traffic management and the resource allocation strategies and the efficient buffer management. The framework ensures efficient, reliable, and cost-effective data transmission. So its approach meets the demands of the data-intensive applications, provide a robust solution for large volume data transmission in one environment. Okay, and that's all. Thank you.
Greg, you have a question?
Greg Mirsky Erickson. So if I understand correctly, the objective of your investigation is to provide bounded latency and low packet loss rate. How that is different from the subject of deterministic networking working group?
In our solutions, we focus on the packet loss. Because the factor of the packet loss due to the low throughput and the deterministic networking, and they focused on the latency or the jitter. Thank you.
No, actually, it's all over the above. It's bounded latency, low jitter, and low packet loss rate. So I think that if anything, have you considered discussing this with the DetNet working group?
Okay, okay, I will discuss later. Okay.
I don't understand.
Yes. No, I mean, I just in my solution, in our solution, just focus the packet loss and just leave the factor. Okay, am I clear?
Okay, so you are saying that you are not considering bounded latency?
Not the direct factor, the latency. Our direct factor is the about the throughput and the packet loss.
Okay, okay. Let's take it to the list. Thank you.
Okay, thank you.
Okay, good afternoon. On behalf of the co-authors today, my presentation is a couple of use cases for high-performance wide area network, which we believe currently failed to address the new requirements from the use cases. Okay. Let's go back to the first page. Okay, thank you. Okay. When we're talking about high performance wide area network, simply because we believe the use cases we raised in the draft in these slides require a higher performance than that provided by the current wide area network technologies, because there's massive data transmission through the long distance to collection, such as cloud storage and backup of industrial internet and data and digital twin modeling, something like it. So the industries lead to solve the problems such as which may result from long distance to slow feedback and coarse grained, node balanced, and node throughput, and so on. That's why we call this high performance to wide area network that achieved effective high throughput transmission. Okay. We have two scenarios. Number one is the distance transmission between two systems. Actually, it could be among multiple sites. We set 1,000 kilometers right here as to the as a threshold, but not exactly. Actually, the first typical use case is the high performance computing for scientific research, which would generate 60 to 100 gigabits of data every 5 minutes, and requiring data transmission from one laboratory to the remote site for analysis. And when it comes to distributed storage, which would involve the moving data from one storage system to another, and is to maintain the data consistency across the multiple sites. And the third one was the data express service, which requires the task-based data transmission and point-to-point model and high resilience and throughput, with the single data, which might be ranging from terabits to 100 terabits. And the fourth one is the multimedia content production. The raw material data from a large-scale variety show or film with the single transmission of data in the range of 10 terabits to 100 terabits, and so it needs to be transmitted between the data centers or different storage sites. And the last one is the data backup and disaster recovery. The working and backup data centers, actually it's the master and slave data centers, are built in different locations to cause long distance and massive data transmission for disaster recovery. The second service is the DC interconnection among the DCs. It's about the collaborative training across the multiple data centers. In this scenario, it needs to be provided on-demand task allocation to different clusters to sufficient bandwidth and no latency and high throughput and extremely high network availability and reliability for the data centers and communications. The parameters exchanged significantly increased under this scenario, so the amount of data transmission across a data centers, and typically from tens to hundreds of terabits. The objectives and goals for the high performance wide area network. The primary goal is the effective high throughput transmission, which demands higher performance. Number one is the ultra high bandwidth utilization, which leads to the efficient use of available network capacity, the maximized data transfer rates. And the second one is the ultra no packet loss ratio, which is very critical for the high throughput, because according to one of our tests, the experimental data indicates that for TCP, the throughput would dramatically decrease to up to about 90% with the packet loss ratio of 5%. And the third one is the no latency and jitter. The round trip time negatively correlates with the throughput. And gaps for the existing technologies with regard to the massive data transmission over the wide area network. The characteristics for the high performance to wide area network is those 2 points. Number one is the massive infinite flows data with large burst, which always would have to coexist with the concurrent services and the dynamic flows. because the wide area network get involved among multiple sites. So there's a problem where results from the long distances, the multiple hops, and the diversified paths and multiple domains between the DCs. And there's the gaps for the existing technologies. When it comes to the optical fiber the direct collection, which usually applies to the sites which the distance between the sites is limited to less than 100 kilometers. When the distance is larger than 100, actually the cost will be significantly increased. And the DC technologies such as priority flow control there's slow feedback and the high round trip time, latency, and jitter. So the high performance wide area network requires improving the flow control precision. When it comes to near street routing technologies, current network is the passive and unaware of the status of the service. So it requires the coordination with the end systems to make the fine-grained scheduling of the resources. And because the current network resources utilization rate is quite low, particularly in the over the wider network, so it requires the fine-grained traffic scheduling. The long-distance transmission requires ultra-low packet loss and long-distance latency and jitter guarantees. Yeah, that's four. And we actually set up the site meeting at Tuesday after long. Everybody welcome. And any comments and suggestions?
Hi, Dejan Bogdanovic. So DetNet created a document, RFC 8578, which is the use case for DetNet, and they talk about issues that different applications, different industry verticals expect from networks. And they are not that much focused on the networking technology as much what certain verticals like multimedia, then energy sectors need from the networking, what characteristics they're looking for to deliver. And this is a document that provides really well-defined use cases. If you want to take a look for high performance WAN, I would suggest you take a look all the requirements for, I believe there's about 9 different verticals in the document that they are talking about what are the expectations on the networks, from the networks. The other part is that when you're writing some applications and they rely on networks, on connections, not all data is the same. Some data, if you lost the data, can lead to catastrophic events. Some data has to be delivered, but it doesn't matter in what time frame. And some data, if it gets lost, doesn't matter. And in none of your presentations, you did any discrimination of the data for different use cases. And you can find that, I believe, also in the 8578. So that would be a good document to consult and then, make references and say what you could improve compared to that.
Yeah, actually, we strongly believe DetNet is a good technology to address the requirements of use cases, but there is a cost balance that we have to take into consideration. If we deploy DetNet technologies among the wide area networks, the cost will be significantly increased. So we are trying to strike the delicate balance.
The networking cost compared to the, let's say, energy sector loss in case of a catastrophic event is minuscule.
Yeah. Okay. Hi, Greg Mirsky Erickson. I agree with opinion that this seems to be one of the cases for deterministic networking. whether it will use existing solution for the DetNet, namely probably what you point to, DetNet service sublayer, which is using pre-auth. Well, that's a question. But again, I agree that for the critical communication or industrial automation or energy sector, loss of data or out of time delivery is catastrophic. So, you know, the cost would be justified. But again, I appreciate that you clearly pointed out that your objective is to provide bounded latency, minimal jitter, and low packet loss rate, which is exactly the subject of deterministic networking, in my opinion. Thank you.
Yeah. Thank you.
Hong Yi from Huawei, and maybe similar to previous province. And I'm curious how you define high performance here. There are too many aspects to define high performance. So I think the term and the title is still a bit broad, and feel like HP1 mentioned here is doing everything. And so my suggestion is to think of a more suitable word from the perspective of use cases. If you want to differentiate from deterministic network.
Yeah, actually, we will look into the use cases of that networking group. But I, as co-author of that draft, I think the use cases raised in this draft quite different from that. But we will look into it. I agree. Part of the requirements maybe overlap with that networking group.
Thank you. Pengfei, you've got 3 minutes. My proposal would be to postpone this till Dublin unless you want to go through one slide just to explain what it is.
Thank you.
Hello, everyone. Can you hear my voice?
Yeah.
Okay. Yeah, before I start, I need to make it clear that there are some problems with my IETF account. So I cannot log in, so I temporarily borrowed this account to give a speech.
Yeah, please go ahead with the presentation. You only have 3 minutes.
Oh, wow. Okay, okay. I'm Pengfei Huo. I'm glad to share this draft for you, OSF framework for AI network. Yeah. For background, let me quickly summarize the background. As AI training model gets larger and larger, we find that traditional data center network can no longer meet the needs of AI. So we need a new set of architecture to support AI network. In the following is simple AI network traffic characteristics and requirements. Okay, and in general, AI training may have fewer flows, but most of flows are elephant flows with a strong burst. In addition, any link flag ping can have a serious impact on the training task. So AI network needs higher bandwidth, higher stability, and low latency. More details can be found on the link below to view our draft requirements. Here are some typical solutions for load balancing. ECMP allows for fast flow fault switching by distributing traffic across multiple equal cost paths. The disadvantage of this approach is that it creates harsh polarization. In OSF can split data per packet or per cell to every link, which is more well distributed than NTAP hash. Okay.
I think it would be a really good moment to stop. We are exactly on time, and you won't have time to go to it. I don't want you really to spend time presenting to empty room. We will give you a slot during next IETF, and so you could go in details through this. Yeah, my apologies
Okay.
for running out of time.
Sure. Okay.
For the working group, we are having AIDC meeting on Wednesday. That's in context of routing working group, where we've got really exciting agenda for you from Piotr Lobhoff and Eddie from Alibaba. They'll be talking about actually some topics that's very close to what we discussed here: adaptive routing. What do we do in AIDC to actually provide capacity? How congestion control might work? And do join us. And we plan to have an interim because most presentations are converging on the same topic. How do we provide notifications that is high fidelity enough, fast enough, and doesn't consume a lot of resources to notify upstream nodes that there's some event downstream, either congestion, loss of connectivity, reduced connectivity. So we'll definitely do interim in between ATFs, trying to gather. And last comment, try to think end-to-end. In most of these networks, endpoints run congestion control. That's really high fidelity. Either it's DCQCN based or timely based. It usually takes a couple of RTTs to detect there's a failure or congestion or some kind of events. Some of them are intelligent enough also to differentiate between in-network congestion versus in-cast, which is congestion at the last point, so towards the server. So in many cases, this is much better place to deal with congestion rather than trying to deal with it on the network. Those networks are very different than what we've known before. So again, we'll address some of this during IDC, and we'll definitely have interim to talk in detail these topics. And thank you, everyone, and see you in Dublin.
Just pay attention to our RTGWG mailing list where we'll announce the interim date and time.
We need 2 meetings. Getting really too busy.
You don't know. Sometimes it's
No, this stuff